Hi scholars, Ms. Beglin here with your independent video for Unit 2 Molecular Structure, Topic 1 Molecules, Lesson 5 Describing Bonds. So far, we have extensively discussed Lewis structures. And the reason we've been doing this is because a well-drawn Lewis structure enables us to describe how bonds form between atoms in a molecule. Now, as AP chemistry students, our descriptions of bonds are going to get much deeper than single, double, and triple bonds. But before we can dive deeper, we need to understand a little bit more about what atoms actually look like. That way, we can describe how they interact or form bonds. So here we see a picture of the Bohr model of the atom. It's the model of the atom that many of us are familiar with, where electrons are thought to orbit the nucleus in clearly defined energy levels. As we've already learned, photoelectron spectroscopy was a major contribution to disproving the Bohr model of the atom because it revealed that not all electrons in the same energy level have the same binding energy. And so it was like, wait, what's going on here? And we had to refine the Bohr model of the atom. This ultimately led us to atomic orbital theory. Here's the thing though, electrons are really small and they move really fast. And we are fundamentally limited in to what extent we can measure their position in space. This is referred to as Heisenberg's uncertainty principle. This equation is not important. All you need to know is that delta x stands for position, delta p stands for momentum, which is the direction and speed which something is moving, in this case an electron. And basically what Heisenberg's uncertainty principle states is that the better you know the position, the less you know the momentum. And the more you know the momentum, the less you know the position. So you can either know where something is or where it's going, but you can't know both. So then this guy Schrodinger came along and he said, well, if we can mathematically describe the uncertainty associated with an electron's position, we can also mathematically describe the certainty associated with them. Now, the equation itself is not important, but the solutions are key. Solutions to Schrodinger's equation describe orbitals, which are areas within atoms where there is a high probability of finding electrons. So when we say high probability, within each orbital, there is a 90% probability of finding an electron. We describe orbitals using quantum numbers. There are 4 quantum numbers, which I'm going to take you through. N is the principal quantum number. It describes the energy level, or the electron shell. Quantum numbers are a good example of how Bohr's model of the atom was kind of accurate. Because here we have distinct energy levels, which we can call 1, 2, and 3. And in atomic orbital theory, we still have distinct energy levels called electron shells that we can call 1, 2, and 3. The next quantum number is L. It is the azimuthal quantum number. It describes the shape of the subshell. L is always equal to n minus 1. So for our first energy level where n equals 1, L is equal to 0. And that corresponds to our S shape, or our sphere shape. When we move to our second energy level, n is equal to 2, L can be equal to 0 or 1. 0 again being our s orbital, 1 representing our p orbital. And we can continue to move forward to D and F. But the key thing here is that the azimuthal quantum number describes the shape of the subshell. It can be L is equal to 0, which we call S, L is equal to 1, which we call P, L is equal to 2, which we call D, or L is equal to 3, which we call F. Next, we have the magnetic quantum number. It describes individual orbitals in a subshell. M sub L is equal to plus or minus L. So when we have L is equal to 0, M sub L is also equal to 0. And this makes sense, right? It's a sphere. You can only orbit a sphere one way. When L is equal to 1, or a p orbital, we get M sub L is equal to -1, 0, 1. So there are 3 possible orientations of our p orbital in space. Then we get to L equals 2, or D. M sub L will be equal to -1, -2, 0, 1, and 2. So we have 5 possible d orbitals, each with unique orientations. What this looks like is this. So here we have our s orbital, and there is only one of them because there is one orientation. Our p orbitals, there are 3 of them, each with its own orientation. Our d orbitals, there are 5 of them, each with their own orientation. And then we have our f orbitals, and there are 7 of them, each with their own orientation. And finally, we have S, which is the spin quantum number. It describes individual electrons within an orbital. So S can be equal to +1/2 or -1/2. And it describes each electron in an orbital. Remember, each orbital can hold 2 electrons. So if we have a full orbital with 2 electrons, one electron will have the spin quantum number of +1/2. The other one will have the spin quantum number of -1/2. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. Okay. So here we have an energy diagram for our orbitals. We show our nucleus. Our energy is increasing as we move away from the nucleus, which we know from Coulomb's law. And here we actually have the energy levels of each of our orbitals and the number that we have of each. Let's fill out this diagram for a few elements. Hydrogen has 1 electron that is in the 1s orbital. We indicate electrons as little arrows. Hence our 1s1 electron configuration. Helium has 2 electrons that are both going to be in the 1s orbital. Notice how I use a down arrow for the second electron. This indicates how their spin quantum numbers are different. This is how we get our 1s2 electron configuration. Lithium has 3 electrons. 2 of them are in the 1s orbital. A third, or the third, is in the 2s orbital. So we get the electron configuration of 1s2, 2s1. Let's do beryllium. Remember, we fill orbitals in increasing energy. Okay, so with beryllium, we have 4 electrons. The first one will go in the 1s, the second one will go in the 1s, the third will go in the 2s. The fourth will also go in the 2s. And so we get the electron configuration 1s2, 2s2. Let's look at boron. 5 electrons, 2 in the 1s, 2 in the 2s, 1 in the 2p. Hence the electron configuration 1s2, 2s2, 2p1. Let's do carbon. 2 in the 1s, 2 in the 2s, 2 in the 2p. Now you'll notice that I place the second 2p electron in a separate orbital. That's because electrons don't really like each other, so they fill empty orbitals before they start pairing up. So we fill empty orbitals of the same energy before we pair up electrons. Okay. Let's look at nitrogen. 2 electrons in the 1s, 2 in the 2s, 3 in the 2p. Hence the designation 1s2, 2s2, 2p3. Now, by the time I get to oxygen, I have to start pairing up my electrons. And remember, whenever 2 electrons are in the same orbital, one has a positive quantum spin number, the other has a negative one because of the Pauli exclusion principle. Okay, scholars, that is actually it for this video. Please let me know what questions you have. Bye.